So now we are going to set the first derivative equal to 0 for the purpose of finding that c, that critical number. So 3x squared minus 12, when you set it equal to 0, you will end up with x squared equals 4, and x is plus minus 2. So in fact, we did find actually two critical numbers for this function. One is c sub 1, and one is c sub 2. So right now, we all know that f at 2 is 0. We just got the x value such that f prime was 0. And we also know that f prime at negative 2 is 0. So this is a fact. We know it. Now let's go over the second derivative test. It says let f prime at c equal to 0. C, we just got it. In fact, we have two c values at which f prime is 0. Okay, if this happens, as you just witnessed, it did happen actually, then what? Then this second derivative test tells us that the second derivative at c needs to be calculated. I'm going to do it right now. I'm going to find the second derivative, which is 6x, okay, and we have to evaluate the second derivative at c, at the critical number, at 2, at negative 2. So I'm going to say f double prime at 2 would be 6 times 2, which is 12, isn't it? And 12 is what? Is positive, isn't it? So f double prime at c, in this case, f double prime at 2, happens to be positive greater than 0. Then what? The second derivative test states that if f prime at 2 is 0, if f double prime at 2 is a positive value, then f at c is a relative minimum. So now I can say that f at c, which means f at 2, is actually a relative minimum value or local minimum value. And the reason is obvious, because when the second derivative is positive, the graph is concave up, right? When it's concave up, it looks like this, and we have a minimum point, obviously. So we have a minimum point because the point is concave up at that point. And this condition here, it says f prime at 2 is 0. It tells us that the slope of tangent is 0 at that lower point, at that minimum point, which means that the tangent line is horizontal. So making a long story short, f at 2, I need to calculate, I have to plug it here. So 2 cubed is 8, 8 and 5 is going to be 13. 13 minus 24, 13 minus 24, that's negative 11, right? It's going to be negative 11. So I can say the point, let's say point B, coordinates are 2, negative 11. This point is a local minimum point. And I found this using the second derivative test. I didn't construct any charts for the first derivative. Now, similarly, f prime at negative 2 was 0. So f double prime at negative 2 would be 6 times negative 2, which in this case is negative 12, and that is less than 0. So that means that f at negative 2, according to the second derivative test, it is actually a local maximum value this time. And if I call the point A, whose x coordinate is negative 2, you plug in negative 2 in the equation. Negative 2 raised to the power of 3, and minus 12 times negative 2 plus 5, use your calculator, and the answer would be positive 21. There you go. So this is your local maximum point, and point B was local minimum point. Did we construct any charts like the first derivative test in the past lectures? No, we didn't do it. Was it faster? Yes, it was. Is it shorter? Yes, it is. What if f double prime at those numbers is equal to 0? Well, in that case, you can't use second derivative test. You have to use the first derivative test. How would the graph look like? Well, the y-intercept is 5, so this is the y-intercept of 5, and we have a local maximum at negative 2 and 21. So if this is like 21, we have a local maximum. So the graph would look like something like this. and then it's going to cross the y-axis at a y-intercept of 5. So it's going to look like something like this. And then it will cross the x-axis at some point here, going towards the local minimum point. And then it's going to go up back again like this. So it's like a graph of a cubic function. This is the point A. Coordinates are -2 and 21. That was the local maximum point. This one is point B. Coordinates are 2, -11. It was the local minimum point. We're going to have some sort of x-intercept there, somewhere around 3.23 if you use a graphing software. 0.4 roughly is another x-intercept. This one should be -3.6 roughly, around that. So this is how the graph will look like. If you use a graphing software, you can draw a nicer graph. You can use software such as Desmos. What else? Inflection point is not the topic here, but if you want to find inflection point, you will take the second derivative, set it equal to 0, and I think the second derivative is 6x. If you set it equal to 0, x will be equal to 0. So that means that at x equals 0, 5, which is actually our y-intercept, we may have an inflection point. And I think you agree that if x is greater than 0, 6s will be positive. If x is less than 0, 6s will be negative. So even if you construct the chart for the second derivative, you will definitely figure out that this point 0, 5 is actually the inflection point of this cubic function. And frankly, the graph is concave down before x equals 0, and is concave up, as you clearly see, after 0. So this point here, I would say this is the inflection point, I 0, 5. The y-intercept of the graph is actually the inflection point of this function. So the purpose of this lecture was just discussing second derivative test and how it works. It's a substitution for the first derivative test, basically. You can always find local maximum minimum points either using first derivative test or second derivative test if possible. Okay, thank you for your attention and keep practicing. I think section 3.3 right now is completely finished. My next lecture will be on section 3.4.